Hi, I'm Govind Sankar from the Indian Institute of Technology, Madras. I'm going to talk about the general factor problem, parameterized by Treewidth. This is joint work with Dániel Marx and Philipp Schepper. So the perfect matching problem is a good starting point. And in the perfect matching problem, we want to find a solution or a subset of edges such that the degree of every vertex is exactly 1 in the solution. This is well known to be polynomial time solvable. And several generalizations of this problem have been studied, like the B-matching problem or the even degree subgraph problem. These are usually reducible to perfect matching. In 1972, Lawatz introduced a general version called the general factor problem, which is what we'll be studying. And in this problem, you're given a graph, and for every vertex, a set BV. And you want to find a solution such that the degree of every vertex lies in the set BV. So for the purposes of this talk, we'll be focusing on this problem called B factor, where you're given one fixed finite set B. You want to find a solution where the degree of every vertex lies in the set B. So we want to study the complexity of B factor and what makes it easy or hard to solve. And it could be the size of the set or the largest number in the set, but rather unexpectedly, it's the maximum gap of the set. And we'll define the maximum gap in this way. It's the largest D such that at most D consecutive numbers are missing in B. For example, 248 has its gap of size 1 here and another gap of size 3 here. So 3 will be the maximum gap. And Kornejolz in 1988 showed that B factor is solvable in polynomial time if the maximum gap was at most 1. And he also implicitly showed the NP hardness when the maximum gap was more than 1, but he considered 2 lists, which were 0, 3, and 1. But a stronger hardness result was known, not explicitly, but it was known that B factor was NP hard for every list with maximum gap more than 1. And this was from a 2003 paper. So we'll be looking at the parameterized complexity of B factor now that we know the NP hardness of it. And parameterized complexity basically quantifies how one specific graph structure influences the complexity of a problem. For example, you could quantify it on the size of the minimum vertex cover or so on. And we'll be looking at a metric called Treewidth, which is basically a measure of how tree-like a graph is. And for example, a cycle is very close to a tree. It's just one edge away from being a tree. The reason we consider Treewidth is because a lot of NP-hard problems like independent set and coloring are easy to solve on paths or trees, and they're also easy to solve on graphs that are like trees in some way. So Treewidth is defined by a tree decompositions, which we'll get to in a minute. And it was already known that B factor can be solved at time m plus 1 to the 3 times Treewidth, where m is the largest element of the set. And we want to ask whether this is optimal, and if not, can we show a stronger algorithm and a strong lower bound as well? And we show that, yes, it's not actually optimal. We can get an m plus 1 to the Treewidth algorithm, where m is again the maximum element in B. We can also show a matching lower bound. We can show an m plus 1 minus epsilon to the Treewidth lower bound for any constant epsilon. And we base our lower bound on this hypothesis called the strong exponential time hypothesis. And the formulation of SETH that we'll be using is basically saying that there's no delta, there's no constant delta greater than 0, such that CN of SAT can be solved in time 2 minus delta to the n on formulas with n variables. So given this background, let's get into our algorithm briefly. So I mentioned tree decompositions before, and a tree decomposition is basically a graph where a tree where every node has a bag or a set of vertices associated with it. You have some additional constraints on how you can have these bags. And the Treewidth of a tree decomposition is the maximum size of these sets minus 1, right? So this here is, for example, the tree decomposition of some graph, and you can see that there are some connectivity constraints, for example, like all the bags in which B appears must be connected and so on. So we'll not get into that for a moment, but we'll just, I'll just mention that the properties of the tree decomposition ensure that a tree decomposition with degree less than or equal to 3 exists. And that's what we'll be exploiting. So the basic idea of the algorithm is to do a bottom-up dynamic programming. And what you store is all possible states of the vertices in the bag, right? So remember, we are solving B factor, where we're concerned with the degree of the vertices in a solution. So what we do is we keep the states that a vertex can be in all the partial solutions. And observe that that can be at most m+1 states, right? So we only need to keep track of whether the degree of the vertex is between 0 and m. If it's more than m, then we're fine. I mean, it can never be part of a solution. So we can ignore those states. And if you look at any one bag, say of t many, if it has t many vertices, then we have to store m+1 to the t states. And that's what basically we'll be doing. We'll be doing dynamic programming. We'll keep track of this and go upwards. So at a join node, or a node with degree 3 in the tree decomposition, observe that it has 2 children and it gets m+1 to the Treewidth states from each of them. So combining these states in the trivial way will take you about m+1 to the 2 times Treewidth time. But what we can exploit is a recent technique called a fast subset convolution to do these in time m+1 to the Treewidth. Right. So that's all we'll basically talk about for the algorithm, because we want to focus on the lower bound more. Right. So for a lower bound, remember, we want to start from SETH, and so we want to start from CNF SAT. And for reductions like this, the standard approach is to have some sort of a grid with n rows and m columns, 1 row for each variable and 1 column for each clause. And what we do is, at the crossing point of a row and a variable, we check if the corresponding clause is satisfied by this corresponding variable. But this isn't really enough for us. I mean, this is a grid graph with n rows and m columns. And if m is more than n, this has a high tree width. This has a tree width of something like n plus a constant. So even if we can do this, even if we can do all this verification, this doesn't give us the required lower bound, because the tree width is something like n. So you start from SETH, where you assume that there's no 2 minus epsilon to the n algorithm for SAT. And using this, you can only get 2 minus epsilon to the tree width lower bound, because tree width is something like n plus a constant. So we need to reduce the tree width somehow to get the m+1 minus epsilon to the tree width lower bound that we want. And we'll be using some ideas to do this. The first idea to keep the tree width low is from this 2018 paper. And to do the verification at the crossing points, we'll use some ideas from this 2016 paper. So this is what the high level structure looks like, or the simplest way to do it. So we have one row for each variable and 1 column for each clause. And these boxes basically check whether this row satisfies this clause. And what we'll be doing is we'll be storing the assignment of this variable on the edges, right? So if this variable is selected, we'll select this edge into the solution. And if it's not, we'll not select it in the solution. So how many solutions can a column process? It can process only up to like 2 to the n states, because you have n edges coming here, and they can only be in 2 to the n states, right? So we want to do something better than this. What we'll be doing is we'll have m edges from each vertex, m edges to the left and m edges to the right. Now, if you look at a column, if you have n rows, it can process something like m+1 to the n states, depending on the number of edges. So in here, 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 and so on. This is what we'll basically be doing. So given what we'll do is we'll come up with a bijection between assignments of variables and states of vertices, basically. So we'll group q variables into n by q groups, and we'll take g vertices, right? So for these g vertices, each of them can be in any state between degree 0 and degree m, right? So if we choose q and g such that 2 to the q is something like m+1 to the g, that reaches our tree width goal that we wanted, which was n by log m+1. And this sort of like works out. So the only thing that needs to be done is to somehow ensure that the information of the states is being transferred along the row. And we'll do this also with these gray boxes. We'll call them relations because they somehow encode a relation over the edges incident to the box. So what it could do, for example, is if it has L edges coming in from the left, it'll ensure that M minus L edges go in to the right. And that forces somehow that L edges are chosen here and so on and so forth. And also, apart from doing this, what it'll also do is it'll take the state, which is the number of edges that are chosen in the solution, and it'll verify whether this state satisfies the corresponding clause of that column. So if we can do this, then we are practically done, right? So we'll postpone how we can do this checking and how we can do this transferring of information later. Basically, if we can do this, then what that means is that we can show a lower bound. And we'll call this intermediate problem the B factor with relations problem. And for the B factor with relations problem, we have our required lower bound because, as I said before, the tree width is something like n divided by log of max b plus 1. And the math sort of works out. If you assume that you have an max b plus 1 minus epsilon to the tree width lower bound for this problem, B factor with relations, then you can, through this reduction, you can argue that you can get a 2 minus delta to the n lower bound for algorithm for SAT. So this ignores a lot of issues. For example, there are some rounding issues and some parity issues. For example, 2 to the q need not be exactly n plus 1 to the g and so on, but we'll ignore that for now. So now what we need to do is we need to somehow encode those relations, right? And how we can do them is through a process that we'll call realization, right? So for that, what exactly do we mean by relation? We mean that it's a bijection between binary strings of a relation and solutions of a graph. For example, we say that a node with degree 3 achieves this relation if the only valid solutions are the ones that choose exactly one of the 3 edges, right? So with that, we're done with relations, but we need to somehow get them. And we can really get them through vertices of set B, right? Remember, we want to reduce to an instance of B factor. And in B factor, you only have relations of node of set B. You need not have this particular relation. So what we'll instead do is we'll realize those relations through some complex graph containing nodes with just the set B. So for example, this is what we'll be doing. So if this blue node here is encoding some relation, what we'll do is we'll replace it with a graph. And since this blue node has a degree of 6, we'll have a graph with 6 edges that have only one endpoint so that it can sort of fit nicely to this. And we'll call these edges with just one endpoint as a dangling edge. And we'll say that this graph realizes this relation if there's a bijection between binary strings in the relation and solutions of the graph, right? Just to note, realizations don't really change the existence of solutions because we define them in such a way. Right. So now we need to find out how to realize arbitrary relations. And I'll not get into too much detail on that. I'll just say that for any fixed finite set B with maximum gap more than 1, we can realize any relation subject to some parity constraints. And we can do this if we can do 2 things. One is forcing an edge, and the second one is realizing EQ nodes or equality nodes. So what's a forced edge? A forced edge is basically an edge that's always in the solution, that's always forced to be in the solution. And an EQ node is a node with the relation such that either all of its incident edges must be selected or none of it must be selected. So it's somehow an equality relation. So the first one, or a forced edge, can be realized in a simple way. So remember, in the decision version of the problem, we are assuming that 0 is not in the set B. Because if it was, then there's the trivial solution, which is the empty graph. We don't want that. So since 0 is not in the set B, then that means that in any solution, there is a minimum degree for a vertex. That's what we'll use here, basically. So you take a clique of size minimum of B plus 1. You split one edge into 2 dangling edges. And so now you have a graph with 2 dangling edges, and every vertex in this graph has degree exactly minimum of B. So the two dangling edges are always forced to be in the solution because every vertex in this graph has to be exactly minimum of B. And observe that we are forcing two edges at once. It's possible that because of some parity issues, we're not always able to force a single edge, but that's okay with us because we can still realize something called an even relation, and that's fine with us. The second step is to realize an equality node. And an equality node can be done the following way. You take a node and you force A edges using the previous construction, right? Where A is the integer such that there's a gap between A and A plus D plus 1. So remember, you have nothing between A and A plus D plus 1, but both of these numbers are in the set B. So you force A edges to a vertex and you add D plus 1 dangling edges to it. So now the two solutions you have are choosing no dangling edge, in which case this vertex will have degree A, which is fine because A is in B. Or you can select all the dangling edges, in which case the vertex will have degree A plus D plus 1, which is also fine. But none of, there's no in-between solution here because there's a gap between these two numbers. And once you have an EQ equality node of arity D plus 1, you can sort of chain them together to get equality nodes of arbitrary arity, subject to some parity issues, which we'll again ignore. So that solves the decision version. We can realize arbitrary relations in the decision version. Now we look at the maximization version. So in the maximization version of B factor, we want to find the largest solution such that the degree constraints are met. And we want to show a similar lower bound here. But the difference here is that we can assume that 0 is also in the set, right? Because some in a maximum solution, it's possible that some vertices have degree 0. And the process is the same as before. We can just need to show that we can force edges and realize equality nodes. But the notion of realization changes slightly in the maximization version, and the reason will be clear in a minute. Like before, if we can force edges, we can do the same process as before and get an equality node. So the main idea here is to first be able to force edges. But the problem here is that forcing does not really work out directly because since 0 is in the set, the empty set is always a solution. So we'll do this in a tricky way. What we'll do is we'll exploit the gap in the list. Remember, we're still assuming that the list has a gap of size at least 2. So let's take, for example, B being 0, 1, and 4. So there's a gap between 1 and 4. So what we'll do is we'll take 4 regular graphs with, say, 2 dangling edges. So there is an optimum solution here, or the maximum solution here is to pick all edges. Since this is a 4 regular graph, the degree constraints are satisfied. Now suppose you miss one edge. One edge is somehow not in the solution. Because there's a gap between 1 and 4, this vertex can't have degree 3. So it needs to lose 2 more edges, or it needs to lose at least 1 more edge. Say it loses this edge. So now this vertex has degree 3, and that's not possible. So it needs to lose at least 1 more edge. So this sort of has a chain reaction effect here. And this process can terminate only when you get a cycle, right? So what we'll be doing is we'll be using high girth regular graphs, right? So if we ensure that the length of the shortest cycle is large, then we can ensure that if this edge is not chosen in the solution, there's a large penalty. That is, you lose a lot of edges in the maximum solution. And since in the maximization version, the question is to find a solution of, say, at least some k edges, this can sort of help us force edges in some way, right? And like before, you can do the equality gadgets in the similar way. Now let's look at the counting version. So in the counting version, again, we want to show a similar lower bound, but the difference here is now that we allow 0 in the list, and we also allow the maximum gap to be smaller than 1, right? This is pretty clear because, I mean, we started this talk with the perfect matching problem, and the perfect matching problem can be seen as one factor, right? Where B is exactly just 1. And we know that the perfect matching problem is counting perfect matchings is really hard. And so we don't expect these problems to be easy in any sense. So, but the problem is that it's not immediate how we can realize relations. Even if we can force an edge, we'll also need a way to realize equality nodes. So we'll do this through interpolation and something called the Holland framework. So the Holland framework is basically a set of problems that can in some sense be seen as a generalized version of B factor with relations. The generalization here is that you have edge weights, and you, instead of counting the number of solutions, you sum up the weights of all possible solutions. So this is well studied, and it's a problem of independent interest. And B factor with relations can be seen as a Holland problem where vertices have list B, or rather the relation Hamming weight in B. And you also have nodes with arbitrary relations. What we'll do is we'll replace the relations with nodes that force edges and also equality nodes. And using interpolation, we can force edges and realize these equality nodes. So I'll briefly describe how we can force edges via interpolation. Using a similar argument, you can say that you can show that you can realize these equality nodes. Right, so suppose you have a gadget h of k with one dangling edge, such that it has p0 of k solutions when the dangling edge is not selected and p1 of k solutions when the dangling edge is selected. Then the number of solutions for the entire graph will look something like this. If the graph has t of these gadgets, your number of solutions will look something like this, where ai is the number of solutions of g when I gadgets select their dangling edge. What we want is AT, that is when all the number of solutions when all the gadgets select their dangling edge, or in some sense, the dangling edges are forced. So you can rearrange this term a bit, and you can get something like this. This looks familiar to us. This is basically a polynomial in this term, p1 of k by p0 of k. So what we can do is if we can construct t different graphs, h of 1, h of 2, and so on up to h of t, with distinct p1 by p0 values, we can recover AT. And AT is basically what we want. AT is the number of solutions when all the dangling edges are chosen, or rather all those edges are forced in some sense. And that brings us to a conclusion. So we should briefly describe the algorithm for a B factor. But that algorithm also works for a general factor when the vertices have different lists. And the running time of that algorithm will be n plus 1 to the Treewidth, where m is the maximum integer across all sets BV. And we also showed a lower bound for B factor. We showed that there's no m plus 1 minus epsilon to the Treewidth. Lower bound for the decision version of B factor and minimization version also works out. And in those cases, we'll need to assume that 0 is not in B and the maximum gap is more than 1. In the maximization version of B factor, we made that the maximum gap of B is more than 1. In the counting version of B factor, we don't really need any assumption other than the fact that B is not trivial, that is just 0. So I'll also mention that these results also go through for a different metric called the path width. And path width is in general larger than Treewidth. So that is a much stronger statement. And we can also talk about another metric called Cutwidth. And we can show that there's a 2 to the Cutwidth algorithm, and there's a 2 minus epsilon to the Cutwidth lower bound for general factor. And yeah, that brings us to the conclusion. Yeah, thank you.